Okay, everybody. How you doing? It's good to see you here Monday for an off-schedule seminar. I'm very pleased to present Farouk. Many of you know from the last several months, half year. As you know, Farouk's at UC Boulder, works on interpretability and machine learning, and is going to present some stuff that might be familiar to some of you, and some stuff that's going to be new to pretty much all of us. And I'll hand it over to you. Thanks.
Okay. Thanks, Dan. Okay, so yeah, it's good to be back. So I'm going to talk about design and evaluation of effective, interactive, and interpretable machine learning. Okay, so I want to start by talking about humans and machines and their abilities. Humans and machines actually have complementary abilities. Us as humans usually turn to machines to help us understand our large data sets and induce structure from those data sets. But there are things that we are actually good at. We are very good at inducing abstract knowledge from our experience and transferring it across different domains. My goal in this talk is to show you that an effective collaboration and interaction between humans and machines is very beneficial. I'm going to present examples of systems that brings humans and machines together to help humans complete specific tasks better and faster. I'm going to also talk about experiments that we have run to better understand humans' behavior when they are exposed to machine learning models, with the hope that that can be served as a guide for designing next-level machine learning and machine learning-based systems. So I'm going to start by talking about text analysis. Nowadays, there's a large amount of data in the form of text available. Every second, thousands of tweets get tweeted, hundreds of blog posts go online, and a massive amount of data in the form of text gets uploaded on Facebook. And many times, we want to understand what's going on in these documents. So definitely manually exploring all these documents is impractical, so we turn to automatic text analysis methods such as document classification to help us get these data in an organized fashion and get the information that we want faster. So these algorithms have been studied a lot, and they have been used with great success, but they still require some amount of manual human effort. So let me remind you of classification, highlighting the human aspect. So these models get as input training data, which is basically a set of labeled documents, and they learn a pattern. And then we can input to them a set of unlabeled documents, and they will predict a label for each one of those documents. Now, this all sounds great, but the problem is how do we get the training data, which is the labeled documents? That is where the human supervision is required. A human experts need to look at all these large document collections, come up with label sets, select some documents from those documents, and assign label to those. So this is time-consuming, it's expensive, and it requires human expertise. So what do we do about it? There has been some solutions proposed. The first one is using crowdsourcing, where you have a set of non-experts do the labeling for you, and there has been a lot of research in the area that if you are careful with the task that you design and the way that you analyze your data, you will get data from these non-experts that experts agree to a good degree. The other approach is using active learning, where you select the most beneficial documents for the user to label next, and then you ask the user to label those documents rather than having them randomly select documents to label. So the way that these algorithms work is that you start by training a classifier on a very, very minimally labeled data, and then the classifier selects a document that is confused about its label. But the idea is that if the user spends their time on labeling this document, we can train a classifier faster. So we query the expert looks at that specific document, assigns a label to it, we get that document, add that to the training set, and we keep doing this until we either run out of resources or we are happy with the training set that we have. So this seems great, using crowdsourcing and active learning, but things get more complicated when we don't know the label set. What if we don't know what to label the documents with? So we started thinking about this problem, and when we think about this more deeply, we find that the reason that coming up with label sets is hard is that annotators usually lack global knowledge about the corpus when they start labeling documents. So we want to provide them with an overview of the corpus so that that can guide them to generate label sets that can be assigned to all the documents. And that is exactly what topic models do. So I'll remind you of topic models. These models take as input a set of unlabeled documents, and they output topics, which are basically distribution over words. And by looking at these topics, you get an idea of what's going on, but what are the overall themes that are happening in the corpus. So for example, if we run topic modeling and generate 50 topics on a decade worth of New York Times, these are 3 out of 50 topics we get. And this basically gives us an idea of some of the articles in New York Times are about technology, some are about business, and some are about entertainment and art. And these models also output a distribution of topics for each document so that you can understand the content of each individual document better. So researchers have designed interfaces that uses these topic models to help people navigate through large document collections and understand them better. But while there has been evaluation of whether people understand a specific visualization of individual topics better or not, there has been no systematic study, no empirical study of whether these interfaces can help people do specific tasks that require exploring of the document collection and large corpora. So our idea here is to use similar interfaces to help people induce label sets that can be applied to large document collections so that then we can use that as input to our classifiers. So we designed a system called ALTO, Active Learning with Topic Overviews, which brings topic models and active learning together to address the issue with the lack of both global knowledge of the corpus and local knowledge of individual documents in the corpus. So we use topic overviews to expose large themes that are happening in the corpus and aid label induction. And then on top of that, we use active learning to direct users to specific documents that would be most beneficial for them to spend their time on. So this is how our interface looks like. The main part of the interface is divided in 2 columns. You see topics, which are basically displayed as an ordered list of words, and then documents are organized by their topics. So rather than having a random list of documents in a random order, we now are organizing documents in terms of their topics. And on top of that, we have this active learning component that at each point, we point the user to a specific document to label. So we have 2 main hypotheses here. The first one is that we think that if we show overviews of the corpus in terms of topics and we show documents organized by their topics, that would be more beneficial than just showing the user an unordered list of documents. And our other hypothesis is that when we have an active learning that actively suggests documents to label next, that is going to be more effective than having the user randomly look at the documents and label them. So to test for those hypotheses, we designed a 2x2 between subject-user experiment where we have 2 factors, document collection overview and document selection. So the baseline is where we don't have topic models. In other words, we just have an unsorted list of documents, and we don't have active learning to select beneficial documents to label next. In other words, the selections are random. And ALTO is where we have both topic models and active learning. We are showing them topic overviews and active learning selections. And the other 2 conditions is where we only have active learning, no topic overviews, which is basically the traditional labeling with active learning, and the other one is where we only have topic overviews, no active learning selections. So this is how the system looks like in the list overview. We don't have the columns anymore. The user sees a random list of documents in these conditions. For the active learning selection component, this is basically a way for the user to move around when they are exploring the documents and select documents to label next. And for the sake of consistency in the interface, even for the conditions that we are not using active learning, we still point the user to one document, but this time this is random, not active. So the way that users create labels is incrementally as they are going through documents. So when they see a document, this can be either the ones that the selection component points them to or something that they decide to look at. They will see the document text, and they will also see the label that has been assigned to the document. And this could either be assigned to it manually by themselves or by a classifier automatically. And then they look at the current label, and they either approve the label, the existing label, or if they decide to choose, if they decide to update it, they choose an existing label and assign that to the document. Or if they think that there is no existing label that is a good match for this document, they create a new label and assign that to the document. Yes?
When the user's instructed, like, how are they told what you mean by label and what's a good label and what's a bad label? Sorry if you missed that.
No. So that's a good question. So in our instructions that we provided to the users was that you are seeing these documents, and your final goal is that if you want to get all the documents that are related to a subject that you are interested in, you want to be able to get them. Now, you don't have to label all of them. There is this built-in classifier that will help you get these in an organized way once you come up with labels that you are interested in and assign some documents to those labels. So they have the freedom to choose their labels. Yes?
Does the active learning use the topic model at all, or it's not?
That's a very good question. It does. So I didn't go over the details on the active learning suggestions, but because we are showing these documents organized in their topics, we want the documents that are showing up to be somewhat related to one of the topics, because otherwise it will be confusing. So we have a new strategy for active learning that we are basically weighting the entropy in traditional uncertainty sampling with the probability of the prominent topic in each document, so that we get documents that are both confusing to the classifier and somewhat match one of the topics in our system. Yeah. Yes.
And the classifier that you're talking about is supposed to end up classifying documents according to these labels that are provided by the user?
Yes, exactly.
Okay. What's the rough number of different labels you're talking about?
So we didn't tell the users exactly how many labels they need to create. There are 20 gold labels in the data set that we are using, and we told the users that, well, create however many you want, but you should probably not go over 40 or 30, yeah. Yes?
So in all treatments, the topic model is being used, but the user only sees the topics in some of the treatments? Is it?
No. So in two of the conditions, in these conditions, topic model is not being used. So they are only seeing a random list of documents.
But the classifier is using the topic model in
Oh,
all.
yes. The topic features are used in all of the conditions.
Right, so the conditions only vary in terms of what information the user sees, not in terms of how the classifiers work.
And the active learning, yes. So the active learning strategy that we are using to point the user to the next beneficial document, that is also different across different conditions. Because like Jake asked, we want the documents that the active learner chooses in the topic conditions to be somewhat related to one of the topics, so that's also different. But yeah, the classifier is using the same features. Okay. Okay, so for our data set and for our experiments, we wanted a data set that has good gold labels associated with the document, so that we can evaluate the labels that users create. So for that reason, we used Congressional Bills dataset. The gold labels for these documents have been vetted over so many years with so many political scientists, and they have high agreement on these labels, and they actually take labeling a lot more seriously than computer science people do. So we trust these gold labels a lot. So for topic modeling, we generated topics using LDA, and for classification to be used for both active learning and also assigning automatic labels to documents, we use logistic regression. So we went to run a user study. We hired 40 people on the freelance platform Upwork, where you can get in touch with individual professionals, and usually communicating with these people and instructing them on doing a specific task is a lot easier than crowdsourced platforms such as Mechanical Turk. So we assigned each one of these participants randomly to one of the 4 conditions, and after they were instructed on how to use the system and what the different features are, they had 40 minutes of interacting with the system and coming up with labels and assigning them to documents. So just to give you an idea of how the labels that users create look like, this is one of the bills in our data set, which is clearly about transportation and TSA policies. And not surprisingly, the prominent topic for this bill has words metropolitan, career, and rail. And examples of labels that people create include security, transportation, and infrastructure. And actually, the gold label that is associated with this document is transportation. So because for evaluating, because we are giving the user the option to create their own label sets, we cannot use metrics such as precision recall or accuracy. Instead, what we do is that we look at the clusters that users create and compare that to the clusters of documents in the gold set. And so evaluating clustering is hard, but we measure several metrics and we find consistent results. I'm going to show you results for purity metric, where the basic idea is that if the documents that the user has put in a set as a label, say like transportation and infrastructure, are associated with very few gold labels, then the purity will be high. And otherwise it will be low. It goes from 0 to 1, 0 for random assignment and random clustering, and 1 for perfect clustering. Okay, so this is how our results look like. On the x-axis, we see time. So like I said, the user had 40 minutes of labeling. We are looking at the training set and how good a classifier we can train with those training sets in intervals of 5 minutes. And then we look at median purity over the participants in each condition. So for the baseline, they don't have any topic model, no active learning. Well, they are improving over time. When they have active learning suggestions to help them, they are improving over baseline. When they only have topic models, no active learning selections, they are actually improving over traditional active learning. And when we add topic overviews and brings it together with the active learning, they are improving over all the conditions. Now, there are a couple interesting things that I want to emphasize here. One, when we bring topic models and active learning together, we are able to train better classifiers faster. The other interesting thing that is happening is that active learning on its own is providing an initial benefit. So this basically means that if your annotators have, say, 15 minutes or so, you should probably not bother with using topic models, because that's just additional information. People need time to digest that information. And using active learning is better if your annotators have very limited time. But otherwise, topic models provide a benefit. Another thing that I think is really interesting is that topic models on their own are outperforming traditional active learning setups. So I think this is very interesting because people have used active learning to help them label documents faster for decades, but the results of our user study shows that topic models are actually more beneficial than using active learning on their own. Yes. No, so it's a measure of seeing how pure the clusters of documents that users create are compared to the gold clusters. So the labels that users create are different than the labels that we have in the gold label. So we cannot use measures such as accuracy. But we look at the sets of documents that users create and see how good that matches the sets of documents in the gold. I don't think it's accuracy. Can you repeat that?
So you don't do exact matching, but match labels different course or matter.
Yeah.
So topic modeling has a destructive effect at low time periods. So red versus turquoise, kind of.
Yeah. So in the beginning, yes. Okay.
Why is that?
So I think it's because people need time to explore topics and understand them and figure out how they can use them. So they just need some time to digest that information. Whereas the red curve, which is active learning only, they just see a random list of documents and there is this smart component that points them to documents that is giving a good diversity for the classifier. Yeah.
Do you know if it's because they're just labeling fewer things per minute in the beginning there, or if they're sort of doing the same amount of work but it's lower quality?
I think they do the same amount of work, the same amount of labeling. Yeah. Yes.
So how good is this? If fair is 0.5, how good is this?
So you can think about it the way that the label of 50% of documents match the gold labels, gold sets of documents.
Pretty good.
For 40 minutes on a large data set, I think so. And I'm going to show you an additional analysis that we did that would make it more clear. Yes?
I'm wondering if another possibility for what's going on at the beginning with topic models is that when you arrange the information that way, people start labeling a bunch of documents from the same topic, and those all maybe tend to have the same label, so you're learning like that one label really well, but you don't have information about it.
It could be. We try to avoid that issue by first instructing them to cover as many topics as they can. And we had like this slider that showed them you have covered 40% of topics. And the second one is the active learning should probably try to help them avoid that, but it could be the case where you have topic models and no active learning, yes. Okay, so so the evaluation that I just showed you looks at the training set that the users create and whether we can train a good classifier with that training set or not. But a reasonable question to ask is, do the labels that users create actually make sense? And are users able to create better, higher quality labels in one condition compared to the other? So to test for that, we designed a kind of a post-hoc crowdsourced study that where we compare the induced labels across conditions and see whether another set of people think some of these labels are better than the other. And for completeness and as a baseline, we also include a set of labels that are automatically generated with no humans in the loop and assigned to these documents based on their prominent topic. So what we do is that we select 200 documents at random. And for each one of those documents, we select one participant from each of the conditions, again at random, and we look at the label that is assigned to the document. And then what we ask the users to do is to tell us which of these labels best represents the content of the document and which of them worst represent the content of the document. And then we look at the number of best votes and worst votes that each one of the labels of each one of these conditions get. So this is how our results look like. We see the number of best and worst votes that the labels of each one of the conditions. And what we see is that the labels that people created when they had topic overviews, information, and active learning received the most number of best votes and the least number of worst votes, which basically means that people thought that these labels are a better match for the content of the documents. And the very interesting thing that is happening is that automatic labels are actually doing really good. So the quality of them is impressive, and they are actually getting roughly the same number of best votes to the conditions that you don't have the topic information, where you only see a list of documents. So these are really, really impressive labels. But what we show is that when you provide the users with topic overviews, they are able to improve upon that and generate better labels. Yes.
Auto means regular LDA.
Sorry, what?
I missed what auto means.
Oh, yeah. So it's a method to automatically assign textual labels to topics based on their top words, and then we look at each document, look at its prominent topic, and assign that label to that document. Okay, so far I showed you this system that we had designed that brings some machine learning tools and help people label documents and create training sets that we can train classifiers with them faster. And so an interesting thing that we found was that different techniques would be more useful in different scenarios based on your resources. You should basically look at the resources that you have and decide which technique you want to use if you want to label your documents. So the next step for us is to take a similar system like Alto that I just showed you and apply it on a real-world use case. So the evaluation that I just showed you, we did it on a data set that we already have the labels for them, and we kind of want to see whether people can recreate training sets that can recreate the gold sets of documents that we have. So we wanted to see whether we can apply it on a real-world use case that people want to find relevant documents to a subject of interest or do specific tasks with it. So the specific use case that we are currently working on is understanding science policy and innovation. And so we are looking at funding agencies such as NSF, and these agencies are usually asked questions such as, how much are you spending on a specific area of research, or what research topics are you funding on a specific area of research? And they need to come up with convincing answers to those questions. And this requires them to look at all of the grants that they have funded and come up with good answers. And what we are currently looking at is whether we can use similar systems to help them find answers to those questions faster. And so we have taken the system that we had for Alto and kind of updated it for us to help users come up with answers to these questions. So we are still showing people documents organized by their topics, and we are also letting them query for specific phrases to find relevant documents to a specific area that it asks in the question. And then once they do this labeling, marking documents as being irrelevant or relevant, they can review all the documents that they have marked as relevant or the classifier thinks are relevant and come up with an answer. And similarly, we have this active learning component that periodically suggests some documents that is confused about whether they are relevant or irrelevant, and tries to find, tries to get a good sense of what users think as relevant or irrelevant to help them answer these questions. This is something that we are currently working on. We are trying to collaborate with experts in the area to give us gold answers to these questions so that we can then go ahead and run the user study. Okay, so that brings me to the second part of my talk. So I spent some time explaining these systems that brings machines and humans together and help them complete specific tasks. And when we talk about this sort of interaction between humans and machines, it's natural to think about interpretability, which has gained a lot of interest recently in the machine learning community. And so in this part, I want to dig more deeply into the issue of if we want to design a system that is that humans can interact with, how can we proceed to design interpretable model, and what does it mean exactly when we want to have an interpretable model? So when people want to design models that are interpretable, they usually have two approaches. The first one is where they try to design models that are intrinsically simple. So models that you can see the effect that each of the features or interaction of features have on the output. Or they try to provide post-hoc explanations of how is it that the model has made a specific prediction for a specific data point. Now, looking at these examples, it's natural to ask what is it exactly that makes a model or explanation simple or interpretable. And when we think about it, it becomes obvious that because machine learning is being used in many different domains with many different people with different backgrounds and different levels of expertise, it's really hard to come up with a unified definition of interpretability or simplicity. So during an internship that I did here this past summer, we started thinking about this problem, and we found that part of the reason that makes interpretability hard to define is that it's not something that can be directly manipulated or measured, but rather it's a latent property that is affected by several factors, such as the number of features, whether the model is linear or not, whether the model is black box or not. And then that, in turn, affects people's ability to trust the model, debug the model, understand how the model is working, and a lot of other things. So when we look at this more carefully, we see that the factors that affect interpretability are properties of the model that you design, but the outcomes are properties of human behavior. So it's really important to bring humans in the loop. And if we want to understand interpretability, we need to understand humans' behavior when they are exposed to these models and they are supposed to do tasks with these models. And run randomized human experiments to understand the effect of each one of these factors on the left on humans' behavior on the right. So we designed an experiment that we particularly looked at two specific factors that are thought to make models more or less interpretable. One is the number of features, and the other is whether the model is black box or completely clear. And then we looked at people's ability to simulate the model's prediction, people's ability to trust the model, and people's ability to detect model's mistakes, and how that is affected by these two factors. So we designed a user experiment, and we wanted to see when people want to complete a task with the help of a machine learning model, how do these two factors affect their ability to do the task. And the task that we designed was a predictive task where the users were asked to predict the prices of apartments in New York City with the help of a regression model. So in addition to a baseline where the users don't have access to a model, we have 4 conditions. I'm going to point to differences in these conditions. So the models on top use 2 features, while the models on the bottom use 8 features. The models on the left are clear, so you see all the coefficients of the regressions and what sort of math is going on there to make the prediction, while the model on the right is completely black box. So that brings us to 4 conditions where we have a clear model with 2 features, clear to black box model with 2 features, black box 2, and similarly for clear 8 and black box 8. And one important design factor that we have here is that all the users in all the conditions see the exact same apartments, the exact same apartment properties, and they see the exact same model prediction. So that is, we specifically chose the examples that the 2-feature model and 8-feature model make the same prediction rounded to the closest $100,000. So this is very important, and this lets us understand that if there is any difference in people's behavior across different conditions, we can say that that is because what they are seeing in the presentation of the model. So we ran a sequence of human subject experiments that I'm going to walk through the results. The first one that I'm going to talk about is where we asked people to predict New York City apartment prices. So we ran this experiment on Mechanical Turk, and the users first have to go through a training phase where they see examples of apartments along with model's prediction and the actual price of those apartments to get a sense of how the model is working. And then they move to the testing phase where they have to make their own predictions of the price. So first, we show this apartment, and we ask them to tell us what they think the model will predict. So basically simulate the model's prediction. And then they see what the model predicts, and they have to come up with their own prediction of the price. So following this, yes?
You're asking people to predict what the model predicts, as opposed to asking people to predict the house price.
We are asking both. So the first step, they see the apartment and they see the model. They don't see the model's prediction, and we ask them to tell us what they think the model will predict. So simulate the model. We want to get a sense of whether there is one specific condition that they can understand how the model is making its prediction compared to the other ones. Yes?
Just to check that I'm understanding, you're supposed to multiply the number of bathrooms by 350,000, add a million.
You could do that, but when we designed this experiment, we actually didn't want people to do that. But we are not preventing them to do this.
What does simulating the model's prediction mean? Not that.
So we want to see, so they go through this training phase where they see what the model is predicting. And once they move to the testing phase, we want to see whether they understand how the model is working. So this gives us a way to do that. But you're totally right. They can take out a calculator and, yeah.
Right, okay. So I could, in theory, predict exactly what the model
Yes.
is. Okay. That's what I was asking.
Yes.
So I may have missed this, but in this particular mode, you're only showing 2 things?
So this is the model uses 2 features, the number of bathrooms and the square footage.
Oh, okay.
But we are showing them all the apartment properties.
Okay.
So those
This is the
2...
model. There's not like a mystery. They know exactly. I mean, well.
Yeah, they are actually instructed in the clear conditions where we are showing them the regression coefficients. They are actually instructed that this is a model, this is how it's working, you get this, you multiply by this, add them up.
Hiding parts of it. Sorry. Yeah. Okay.
Yeah.
So,
Yeah.
feel free to defer this. Did you check if, like, asking people what the model predicted first affects their prediction? So, right. So that I can imagine like 2 treatments. One is like you ask me what does the model predict, and what do I think the price is, and then the other way around. What do I think the price is, and what I think the model is.
Yeah, we actually we didn't particularly look at that, but we ran another experiment where we get an initial prediction without showing the model.
Okay.
Yeah.
We did look at that. That was the 3rd experiment, right? When we saw that people's predictions were actually being influenced by
Oh, yeah, but we didn't particularly look whether the simulation error, how that compares to these other experiments. But yeah. Yes?
Those people know about the predictions, why they would predict it wrong?
They do. I'm going to show you the error, the simulation error, and how people don't have perfect results. Yeah. Okay. All right. So following best practice that is becoming more common in the psychology community, we pre-registered our hypotheses. So we pre-registered 3 main hypotheses. The first one is about people's ability to simulate the model. And our hypothesis is that people in CLEAR 2 will be better able to simulate the model. The other hypothesis is about trust, where we hypothesize that people will trust the CLEAR 2 model compared to black box 8 model. And we make this direct comparison because we think about these 2 conditions as like 2 extremes in terms of interpretability. And our third hypothesis is about people's ability to detect mistakes, where there is this weird apartment that the model is making an inaccurate prediction on, and we want to see whether people in one condition are better able to detect that compared to the other condition. So starting with the first hypothesis, which is about people's ability to simulate the model, we calculate the simulation error, and that is basically the absolute deviation of what the user thinks that the model will predict from what the model actually predicts. And this is how it looks like. What we see is that people in CLEAR 2 have significantly lower simulation error compared to the other conditions. But it's not 0, so they are not all of them are taking out a calculator to.
And you also got to save a lot of time to do the calculation.
It is longer for the CLEAR 8 model, where they see 8 coefficients. But so I think it has an effect, at least on the time, but it's not like everyone does this.
Sorry, did you pay for accuracy or pay for response?
We paid a flat rate. Okay. So looking at this, our second hypothesis, which is whether people trust CLEAR 2 more than black box 8. And so we measure trust as the deviation of users' final prediction from the model's prediction. So the idea is that if the user trusts the model, they will deviate from the model's prediction less. And so what we see here is that there is no difference between CLEAR 2 and black box 8. So people are following the predictions of these models equally. So to test for our third hypothesis, which is people's ability to detect models' mistakes, we use the fact that the model is putting a large weight on the number of bathrooms. And when you have a weird apartment setting where you have 1 bedroom and 3 bathrooms, the model will make an inaccurately high prediction. And we wanted to see whether people would be able to pick up on this in one conditions compared to the others. And so what we look at is people's deviation from the model as a measure of trust on this particular apartment only. And what we find is that people who see a clear model are less able to detect that mistake. So they basically follow the model's prediction for this particular apartment more when they see a clear model compared to when they see a black box model. And this is really interesting because you would hope that if you are showing them a transparent model where they can see the weight of different features and they see that, well, this apartment has an unusually large number of bathrooms, they would say that, oh, that might be wrong, so I should probably make another prediction, but we don't see that effect. We see that they still follow the model more. So in the experiment that I just showed you, we were looking at New York City apartment prices, and we got some feedback from our workers that these prices are just too crazy. I cannot wrap my head around this. So we thought maybe we should scale down the prices to be more in line with the median prices in the US and run another experiment. And that brings us to the second experiment that we ran. So we again pre-registered our hypothesis. The first two hypotheses about simulation and simulation error and trust stays the same. This time we made our third hypothesis more precise, that we think that people will follow the model's prediction when they see the clear model more than when they see a black box model on the weird apartment that we had. Yes?
Doesn't that contradict your first finding? Sorry, second finding. So you're saying
So
that
the
people don't trust the clear models more than they trust the black box models,
So for
but they do when it's wrong?
So for the second hypothesis, we and the results that I just showed you, those are for the regular apartments that we had, not the weird apartment setting. So the model is doing reasonably well there. They have different sets of different error levels, but there is no weird signal in the data that would alarm the users that the model will make a wrong prediction here. So we are treating these cases differently. We are looking at them differently in our analysis.
Right, sorry, maybe I'm asking you.
Sorry if I'm not.
So trust is just the closeness of your guess to the models.
Yes.
Yes, right. And you don't find a difference between clear models and black box models overall.
Yes. On the regular examples, we don't find a difference.
But you do find a difference when
Yes.
there are errors.
Yes.
It's the clear ones that do
Worse. Yes.
Okay.
Okay, so again, looking at simulation error, we find similar results with the scaled down prices. People in clear to have a better understanding of how the model works, and their simulation error is lower. We again look at trust, and we compare clear to and black box 8. We again don't see a difference. So the high prices of New York City was not the main factor here that was leading to almost equal trust in the conditions. And on that weird example where you have 1 bedroom and 3 bathrooms and the model is making an inaccurate prediction, we see the same pattern that people follow the model's prediction more when they are seeing a clear model compared to when they are seeing a black box model. So we ran 2 experiments and we didn't see a difference across conditions in terms of trust for the regular examples. So we thought maybe we should look at an alternative measure for trust called weight of advice, which is discussed in psychology literature. And the idea here is that you get 2 predictions of the price from the user, one before they are exposed to the model and one after they are exposed to the model, and then look at the extent to which they tend to change their prediction after they get an advice, which in this case is the model's prediction. So just to give you an idea of how it's different from our previous measure of trust, if the model has a prediction and the user's final prediction is close to the model's prediction, our previous measure for trust will be pretty low, which means that they are trusting the model. But it can be due to 2 facts. If the initial prediction of the user when they were not given the model's prediction was actually very close to the model's prediction and they only slightly changed their prediction, then weight of advice will be low. Whereas if their initial prediction was far from the model's prediction and they drastically changed their prediction, then the weight of advice will be high. So we want to see whether we see a difference in terms of weight of advice across conditions. And then that brings us to our third experiment where we still do it on New York City apartment prices, but this time we changed our design to get one prediction from the user before they are exposed to the model, and then we show them the model, we instruct them on how the model works, and get a revised prediction. Yes?
Is it possible that your final prediction is actually moving away, moving to the other direction?
Yes, we are looking, it is, but we are looking to the absolute value, so it won't distinguish those cases. Yes.
In a previous study, for each prediction, does the subject know the price after they make prediction?
In the test case, no, they don't.
My guess is I may also make similar to be a middle test between this one and the previous one, because if I make a prediction and you tell me the prediction from the machine, I know the truth, then I see the machine is so close to truth, and also maybe some of them also closer to mine, so that can build a trust.
So you're saying that
I learn by the outcome of my own prediction, the models, and the truth, I can build some trust on the model's prediction.
And that's what we were planning when we were designing the training phase. That was our goal. So before they actually start to make predictions of the apartments that they won't see the price for them, they go through this training phase that they see the model's prediction and they see the actual price of the apartment. So they get a sense of how the model is working and whether they should trust the model or not. Okay, so we again pre-registered our hypothesis. This time for trust, our hypothesis was that we think people will trust clear to more than black box 8, both in terms of deviation from the model and in weight of advice. So looking at our old measure of trust, which is the deviation of their final prediction from the model's prediction, not surprisingly, we are not seeing difference here. Looking at weight of advice as an alternative measure of trust and comparing clear to and black box 8, we still don't see a difference. So we ran a lot of experiments, and I just want to give you an overview of our results. So what we found was that people who were given a clear model that uses a low number of features are able to understand better how the model is working and better able to simulate their predictions. But contrary to our hypothesis and contrary to general belief in the community, we are not finding a significant difference in participants' trust in these models. And another interesting thing that we find is that on unusual examples that the model is making and inaccurate predictions, people trust the clear models more than black box models. So these results indicate that, contrary to general belief, simplicity or transparency does not always lead to higher trust. But as easy as it is to jump to the conclusion that interpretability is not important, I just want to emphasize that here we only looked at one specific scenario, one model, one subpopulation of people, only 2 factors, and very few changes in human behavior. In the future, I am excited to play around with, look at other scenarios, look at other families of models, look at classification versus regression, other populations, looking at experts compared to lay people, looking at other factors that people usually think that would make models more or less interpretable, and looking at other abilities that we want people to have when we want our models to be interpretable. I think the important thing is that we need to bring humans in the loop and optimize for their abilities in doing tasks rather than thinking about this as a purely mathematical or computational problem. Think about this more in a more interdisciplinary way and try to understand people, because they are the final end users of our models. And in the long term, I am very interested in using all the insights that we get from these experiments on understanding people's behavior to design new models and new systems that would better fit humans' needs and would be better able to help them complete tasks. So with that, I'd be happy to take any additional questions. Yes.
Could you give some intuition for that interesting result that you only trust the models, the transparent models, more when they're wrong?
You mean on the weird apartment?
Yeah, I mean that's basically the result, right? That you overall you don't trust them more, but somehow you do trust them more when they're wrong.
Yeah, so actually when we were pre-registering our hypotheses for the first experiment, we intentionally did not say which way we think it will go, because if you think about it, it could actually go either way. So if a model is simple, or people can understand how the model is working, if it's transparent, and if they understand it well, they might just trust it because they understand the model. But the other intuition that did not happen based on our results was that if they understand it better, they should be able to detect its mistakes. So yeah, I think that the thing is that is happening is that if it's simple and they have some idea of how it's working, they trust it, even if we are not seeing the
when it's right.
Yes.
So that I just like, I mean, how does this psychology, like, I just don't understand what's changing in your.
So maybe maybe, and I don't know, but this is just my intuition that when they see this totally weird apartment that they just don't have an idea of how the price would look like, and they just have an external source of help. And if they don't have any intuition and they are totally lost, they totally rely on their source for help.
Your N must be a lot smaller for the weird case, right? Is it possible that this is just
What should be smaller?
the number of observations?
Yeah.
Is smaller. Is this just an artifact of noise?
I don't think so.
Size is the same.
Yeah, but for the other experiments we look at.
But were you able to replicate the results with a different sample? Like just
Well,
very robust.
Yeah, but we ran a lot of experiments, and
But the specific observation can be replicated with other samples?
Yeah.
Yeah.
Because it was in study 1 and study 2.
Yeah.
I see.
Same empirical department.
yes.
So one thought about that, it seems like when people, like, if things are transparent, you understand it more, so you might be more willing to be lenient when it does mess up. But you also know its limitations. You don't think it's magical. Like, there was a talk recently where I think, like, like if you produce something, like I think, like we had a talk where someone was talking about documenting how you came up with an algorithm, but it might be biased. Like if you document the algorithm, people might be more willing to say, oh, they didn't really mean to be biased. It just kind of happened that they got bad luck. Whereas if it was a black box, I might just assume, oh, they were malicious. They came up with a biased machine learning algorithm. So sometimes I think just showing it has weird effects. Like you trust it, maybe you're more lenient, but maybe you might also feel like, oh, I know what it's doing. It's not that intelligent. I get it. So I don't give it like godlike status or something. Okay, that was
That's interesting.
I know it's very hand-wavy thought, but it's a thought. Actually, I have a quick question for you.
Yeah.
It seems like there are a lot of things going on in your experiment. Like when I think about people looking at examples, like bad examples, good examples, it's almost like you're testing their ability to like generalize and not overfit, or maybe there's all these things going on. Do you think there's a way to like isolate some of those things and evaluate those separately, like how people react to, I don't know, accurate prediction, and then like an error? Like how do they react to a misprediction or a model's mistake? Like I don't even know how to think of it.
So we intentionally put that weird apartment in the very end to not bias their thinking of the fact that this could happen and the model might make a very bad prediction. So we always showed the examples that the model was doing reasonably, and then showed the apartments, the two weird apartments. So that's we kind of wanted to avoid that. And on the other examples that we were showing them, the apartments that they were seeing in the training set had the same error distribution that, compared to the apartments in the testing phase. So, yeah.
Okay. Can I try again?
Yes.
So I'm just trying to imagine like my own psychology doing this experiment, and I'm seeing a bunch of predictions from a model, and I'm looking at them and I'm like, yeah, seems reasonable, yeah, seems reasonable, yeah, seems reasonable. And as long as it seems reasonable, I don't really care whether it's being explained to me or not, because they just seem reasonable, right? I've got some implicit intuitive model in my own head that I'm using, and I'm looking at these predictions and they seem like ballpark, okay? And then I get one that's like crazy. I'm like, what a weird apartment. 1 bathroom, 1 bedroom, 3 bathrooms, that's insane. No one would ever buy an apartment like that. And so then I have this sort of interaction effect where now it matters whether I'm being given an explanation or not. And if you give me an explanation, I'm like, well, I don't know, it seems crazy, but that's a reasonable explanation. And if you don't give me an explanation, I just don't believe you. And so maybe that's where the differences happen.
Yeah, I mean, it could be. That's an interesting insight. But for the examples that we chose, the error, again, for both training step and testing step, the error was going from 0 to 500,000. So they were seeing examples that the model was making bad predictions. Well, not as bad as the last one, but we showed them those examples to kind of tell them that the model is not perfect. They actually saw that the model was off by 500,000 for some of the apartments. So.
And that's because they were coming from different neighborhoods or something, and that was not.
No, we actually got them from Upper West Side only. So. Yes.
I think there's some another metrics might be interesting to look at, or may also kind of address Duncan's hypothesis. You can measure people's likelihood to adopt this algorithm. If in the cases I cannot make sense what is happening in this case, and the algorithm is doing better, then I might like to more adopt algorithm, even though because it doesn't really make sense to me.
What do you mean by adopting the algorithm?
Like think about you can give a cover story like this machine can help you to pick a price, whether you are more likely to adopt this algorithm to make the prediction for you. Because in a weird situation, I cannot make sense all the numbers, then I may be more likely to adopt algorithm to make decision for me. And in a more interpretable case, by learning all the parameters, I have a better sense of what's going on. I will be less likely to adopt. So all those adoption decisions may be kind of orthogonal to the level whether I trust them or not. It's just whether I think I have the ability to do the task.
Yeah.
Does that make sense?
Sort of. So you're saying that maybe we should design a task that looks at that, whether people might adopt the model to make their predictions?
Just show them 2 predictions made by 2 different models and see which one they pick.
Yes, but that would require, would the models make the same, that's somehow what we're doing, right? Because
I think trust is a different metric than adoption. So because trust relies on my have to understand it, but adoption means whether I want to use this algorithm to make decision. I think these two may be correlated, but still there's some orthogonal space between them. I would expect for the case all the numbers are crazy, I cannot think through what is happening there, I will be more likely to adopt the algorithm. That might explain why in that case there are some significant differences.
Okay, so like if they were to do a task and have them bid on which one of these models they want to use?
You can either have a Likert score, ask them the likelihood you want to adopt this algorithm, to apply this algorithm to make decision for a similar task, or you can give them choices to see which algorithm you want to choose to help you to make decision. I think either way you can better see whether that, because I think that should be easy metrics you can add in addition to trust to see whether that has the differences. Maybe that will interact with the trust and a mediator.
And do you,
We should probably
yeah, okay,
wrap
sorry.
this little thing over,
We
but-
can talk later.
Yeah, you guys can keep going. Thank you. Everybody. Thanks.
Thanks.